So one topic that may not be a focus on the AP exam, but it's also one of those things that, oh, it's fair game. So I do want to mention it, not only because it could be on the exam, but also this topic is just very important in terms of like what's the usefulness of thermodynamics, aside from the fact that it basically dictates the entire universe. But so I do want to basically talk about heat engines and how the second law of thermodynamics is applied to it. So many thermal processes occur naturally in, I'll use the word nature, but what I mean by that is like in physics, thermodynamic nature. What's interesting about how thermal processes work is typically they'll occur in one direction and not the opposite. For example, in nature, maybe you have I say in nature you have a container of gas, but maybe it would be natural for that container to expand, but then it would be unnatural for it to contract. So for example here, hot air, the air itself always flows from a hot object to a cooler object and never the opposite way, right? Because having the opposite occur would violate the first law of thermodynamics because energy would not be conserved. One thing you can't do is break the laws of thermodynamics. If you learn anything from physics class, please let it be that. This guy here, Sadi? Carnot? I'm pretty sure it's called Carnot because he's French, so you don't pronounce the T like you do. That's how it happens in French class. He studied irreversible processes in detail and came up with a lot of mathematical theories about them. So this being one of them being the second law of thermodynamics. All right, so the second law of thermodynamics states that heat flows naturally from a hot object to a cold object and never flows spontaneously from a cold object to a hot object. Sure, you can force it to happen, but it's not going to happen naturally. Okay? So that's the second law of thermodynamics. I do want to talk about heat engines as well. Right? So a heat engine is just a name given to a thermodynamic system that uses this idea from the second law of thermodynamics that heat energy transfers from hot to cold. It uses that in terms of mechanical advantage, right? So it's going to use that heat transfer, that energy transfer, and use that energy to do physical work, right? So Papin? I'm not sure. He is the inventor of the pressure cooker, but he described three basic components of a heat engine. You basically have to have some high temperature, what's called a reservoir, a low temperature reservoir, and an engine containing a gas or steam. So reservoir here, I like to think of it as kind of just it doesn't have to be a tank or anything like that. It's in whatever heat engine we're dealing with, whatever mechanical system we're dealing with, there's a region in which it's hot, and there's another region, the cold reservoir, which is cooler in temperature compared to the hot reservoir, so therefore heat will transfer. And the idea here is what you have doing work is kind of sandwiched in between. Actually, I'm going to go to the next slide. All right. So heat's going to transfer from the hot to the cold reservoir, and this exchange of heat, you're going to use that to do work. So for example, maybe this exchange of heat is going to cause some sort of piston in the engine to expand, and that expanding force then is used to do work. So that's kind of the basic idea here. There's various types of heat engines. I just want to kind of focus here on the combustion engine. Well, for cars, I really don't know much about that, but kind of the simple idea here for the train, you have kind of you have some hot coals that are being burned. So this is your hot reservoir. You've got that energy being transferred to the engine itself, which is water being evaporated into steam, which then pushes a piston that does mechanical work and causes the wheels of the train to turn. The cold reservoir here is actually just whatever is not involved in this. So kind of the train itself, the surrounding air, that kind of thing. All right. In a way, what also is here is the cold reservoir would be the water as well. So even though the piston here is not sandwiched in between the two, it's fine. It's kind of an indirect way of doing a heat engine, but it's still a heat engine nonetheless. You have energy transferring from a hot to cold region, and you're using that in some terms of a mechanical advantage. You can, if you'd like, compute the efficiency for a heat engine. The AP exam actually does not have this formula on there, so I'm just going to mention it and then use it to help explain something else in the future. But efficiency is basically how efficient the engine is at using the energy available to it, right? So this formula here being work over the heat, this heat in the denominator is the total amount of energy that is transferred from the hot to the cold reservoir, and the work there is the amount of work that the engine does. So if it uses all of the energy, then it would that work would be equal to that amount of heat, and you get an efficiency of 1, so 100%. That's not going to be possible because some of the heat is going to be transferred to the cold reservoir, so not all of that energy available is going to be done to do work. So that work is always going to be smaller than, the numerator is always going to be smaller than the denominator, which makes sense. You can't have an efficiency larger than 1. You're always going to have energy loss to the environment, whether that environment be here, the cold reservoir, or, I mean, basically the environment is the cold reservoir. So you're never going to have an efficiency larger than 1. So we could do some problems here, doing some computations with it. I don't think it's going to be useful. But I do want to mention something very important in thermodynamics called the Carnot Cycle. So kind of you can think about engineering and using thermodynamics as a mechanical advantage. So you'd want to design kind of the most efficient heat engine possible. And this type of heat engine is actually known as the Carnot Cycle. So here's a kind of a depiction of a Carnot cycle heat engine in a PV diagram. So basically Carnot did, a bunch of math. It's kind of a long story short. And he found that the maximum efficiency would be this situation. And what's going on here actually is that we have two reversible processes and two, actually this is all reversible processes. But basically, you have a thermodynamics cycle occurring in such a way where you have two reversible isothermal processes and two reversible adiabatic processes. So basically, looking at this cycle here, the process from A to B is an isotherm, and that's why you kind of have this dotted line depicting some higher temperature. And during that process, you have the heat transferring to our engine. Then you have an adiabatic process, so you have a change in temperature. And we get to process C here, in which then you have another isothermal process. So now basically our engine is decreasing in volume, and to which where the temperature is kept constant. And then you have another adiabatic process, which again, you're still decreasing the volume, but you get back to the original state. So if you kind of imagine a piston moving, it'd have to move in such a way where all these things would be possible. So you have to have two isotherms and two adiabatic processes. So the only time heat is exchanged is during the isothermal processes, since adiabatic means no heat is added or removed. So you could compute the total amount of work done by this, and he found mathematically that this causes the most amount of work to be done by a cycle. Right? So when you hear Carnot cycle, just think, oh, that's the theoretically most efficient cycle or heat engine that's possible. And actually, that's all I wanted to mention. This is just a very important concept when it comes to thermal physics. So I did want to mention it, and watch this not even be mentioned on the AP exam. But I thought it'd be good to mention nonetheless. So I hope that was somewhat enjoyable, somewhat interesting. So yeah, thanks.